So thank you for the quick introduction. I'm going to talk to you today all about the imaging side of MRI rather than the kind of spectroscopy side, which we've looked at already, and the time domain side of things, which are both very interesting and what we normally do, actually. So this is the kind of other half of my work, which is on the imaging side of stuff. So a quick outline. I'm going to build on the talks which we've already heard today, and we're going to have a look at some of the basic hardware, some of the principles of MRI. We're going to have a look at specifically how we build up an image for MRI, which is one of the kind of biggest parts of the talk. Then we're going to have a look actually at why MRI is not always the best thing for what we want to do for this project, although I'm going to show you the tricks to make it work, and hopefully we're going to get to see the MRI actually in action at a couple of points throughout. So I've used our system wherever I can, just as to give you a kind of feeling for what it's really like in real life. Okay, so a sensible starting point then is what is MRI, and when I wrote the slide I really realised that what I actually wanted to tell you is what MRI is not, because it makes it a bit easier, I think, to see what's going on. So these are what MRI is not, and these are the things which we've looked at today already. So you've got spectroscopy on the left hand side, so kind of chemical fingerprinting, drop in a sample and this will tell you what's inside. On the right hand side we've got the resonance system spin track there, which is our time domain instrument, and that's going to tell us all about the properties of our samples too. Now, the MRI can do some of those things, but the thing that the MRI is really good at is making pretty pictures. So this is a picture of my brain from when it was young and filled with youthful excitement on an MRI scanner, and this is obviously what they're really meant for, is to scan people and look inside non-invasively and get a feeling for what's going on in the tissues. Obviously, we don't really care so much about that here. We're going to look at how we can apply it for other techniques, and to look particularly obviously at confectionery, but also lots of different fruit and veg and food things. It's a really powerful tool and technique, although it's not used as much, I think, as it could be, but hopefully we're all going to change that. Okay, so obviously you're all probably sick now today already of hearing about protons, but just by way of full recap, I promise I will be as quick as I can. This is our representation of a water molecule. The two little white Mickey Mouse ears are our water, our hydrogen protons attached to an oxygen, which is the thing which we are going to look at in MRI. You can look at other nuclei in MRI. It's not exclusively proton, but to be honest, most of the stuff which we do, in fact all we can do on our system at the minute and on a lot of clinical scanners, is proton. So that's what we're going to concentrate on. If we look specifically, briefly, a more physicsy look at what that atom looks like, this is its kind of probability cloud, but this is not really very useful for us in MRI. I like to think of them as a ball with a stick in, as most people do when looking at a kind of classical description. And this ball has two useful properties to us. One is a magnetic moment, by which I mean it's like a tiny bar magnet, and one is that it has angular momentum, which we can think of as it spinning round like a spinning top or a bike wheel, as the analogy goes. So we're going to represent these with these little balls and sticks. In a beaker of water, as we've heard already, you have this jumbled up order. You stick a big magnet next to them and they all line up against the magnet, except that's not really true at all. What actually happens is, for all of these poor protons that don't line up against the magnet, this one little green one does, and this is the only one in this enormous collection that's actually useful to us. Now, this is such an important point, I thought it's worth making again for the third time today, is actually it's only this one that does anything for us. And all of these other ones just sit around actually being a bit of a nuisance. And so we need to come up with ways to be really sensitive to this one tiny one. So the question always is, well, why? And unfortunately, this chap is to blame for why. Well, not really to blame, but he's the one that worked out why. So this is Boltzmann, and these are some standard Boltzmann statistics. So you don't really need any of this particularly. What I want to show you is what's in this equation, because this is the bit that's most important for us. So the gyromagnetic ratio, which we've met 3 times already today, is unique to a specific nuclei. So we're going to use the value for proton, which is 42 megahertz per Tesla. We then have a constant, can't do anything about that. We've got our field strength in Tesla, which we can change. We've got another constant, Boltzmann's constant underneath, which is fixed, can't do anything about that. And then we've got the temperature. So if I want to get more of those green nuclei than red nuclei, there are only two things that I can change. One of them is the field strength and one of them is the temperature. The colder it is, the more green we've got to red. The stronger the field is, the more green we've got to red. Now, the reason that I want to tell you this is because this is kind of critical to how we end up with the field strengths that we end up with in MRI. Almost always you will see reasonably high field strengths, always above half a Tesla, normally above 1 Tesla. So our scanner's 1.5. And the reason is because, especially if you're scanning humans, you're kind of stuck. I would love to put a human at 0 Kelvin to have an enormous polarization, but people can't survive at that temperature, so you can't change that. And the only thing you can change is B0. So we have to make that big in order to get the biggest polarization that we can achieve. Okay, so in MRI, we do that by having these enormous magnets. So this is our old scanner, and this was 2.35 Tesla. And on the left here, you can see a cross-section of the thing that makes it a magnet. So this is superconducting wire. Oh, that's gone quicker. And actually this cross-section here is how the bar starts out. So they start off with a big cross-section, looking for my camera, like this, with all of these tubes in of superconductor and copper, and then they draw it out, stretch until it turns into either a wire or a ribbon. So our current scanner uses a ribbon, but the old one was a wire. And as long as that is supremely cold, we're talking minus 200 and something degrees, so a couple of Kelvin, it will be a superconductor, which means that as long as we want it to do so, it will be a really big magnet. And it's a really stable magnet, it's a really strong magnet, and it will stay a magnet for, in theory, so Siemens say, hundreds of years without needing anything doing to it. But whether or not that will happen remains to be seen. So, demonstration of the fact that it is indeed a strong magnet. This is a stress ball. This is a tiny washer. It's only this kind of big. And I took a scalpel to the stress ball to stick in this washer so that it was safe to throw a washer at our MRI scanner, because unsurprisingly, it's not a popular activity to throw washers at MRI scanners. So this hopefully makes it nice and safe so that we can chuck it in and see how strong the magnet is. I was then a bit worried that it might pop out, so I wrapped it in Nesco film too, with the hope that it would stay in there for its next little journey. The washer itself is not particularly magnetic, it's just a steel washer, and MR unsafe sticker just to make sure that no one has any problems with it in the future, and then we'll take it over to the scanner to have a look. So here it is on the bed. We're just going to approach the scanner with the bed now. That's just gone over the 50 Gauss line. And in it goes. I was a little bit disappointed with it. I thought it would go faster, so I built another one with a bigger washer. Here it goes. That's the 100 Gauss line. And that was a bit more exciting. So obviously this is the problem with MRIs from a safety perspective. Anything that you take near it that's metal is a projectile, or at least a ferrous metal. And actually it will suck it through. And if you're inside the scanner when it does it, it's bad news time. If we're using them for materials, it's not quite such a problem, but it's a really important thing to consider. So this is 1.5 Tesla. This was a bigger washer, like, there's my camera, like this. And it really will pull it out of your hand very quickly. Okie dokie. So we've got now our big magnet. So what are we going to do with it? We're going to start off by exploiting one of our properties, which is the magnetic moment of our protons. And to do that, we're going to use a technique which we call resonance. So resonance is an important phenomenon. Obviously, it's so important that it's included in the name of all of the techniques: magnetic resonance imaging, nuclear magnetic resonance. And the idea is, if you think about someone on a swing, if you just go randomly shove someone on a swing, they don't get any higher. In order to get them high, you need to push them when they're at the top of the swing. Okay, so we are pushing them in time with how they're naturally swinging. Okay, so that is resonance, and it's exactly the same for our system. we need to be on resonance with our system. So this is Nmr and his famous equation, which underpins everything that anyone ever does with anything to do with nuclear magnetic resonance imaging or otherwise. And the idea is that we have our wonderful constant, again, fixed for protons, and we have our field strength. And if you just multiply the two together, you come out with the resonant frequency of your system. So in a 1 Tesla system at 42 megahertz per Tesla, we would need to be at 42 megahertz to be on resonance. Now, for most systems, that corresponds to a radio frequency, which is why we always talk about RF coils and these kind of things, but it's not necessarily the case that it is radio frequency. So we've got a couple of systems that work below radio frequency in the kilohertz range. They're a lot of fun in their own right because you can actually then hear the sound. So our Earth field scanner is really cool because the frequency range is within human hearing, so you can actually hear it boom as you get the signals, which is really neat. But for what we're going to talk about today, it's almost always radio frequency. Okay, we're nearly there through the same stuff as everybody else's. So this second property then, which we're going to look at, is angular momentum. Now, angular momentum is a weird property which all things have in life that spin round. So I have here a bike wheel, which is a classic thing that spins around, and it gives us a really nice way to look at some of the strange properties that you get from the fact that things have angular momentum. Now, the field of view on my camera is not very big, so I'm going to step back and try not to get tangled. So at the moment, this has no angular momentum because it's just sat still. And in order to have angular momentum, things need to spin round. So to start off with, we will spin round the bike wheel, and I'm going to give it angular momentum. Huh? Yep, good idea. So let me stop sharing the screen, and then you might actually be able to see me. Good plan. There we go, now I'm big. So here is my bike wheel spinning round. Now, angular momentum is a strange property, and its definition actually is that for a thing that's spinning around like this, angular momentum counts as poking out of the end, which is peculiar, but it works for the physics, so we're just going to go with it. So we'll spin it round, we'll give it angular momentum. In a proton, it always has angular momentum. Fortunately, no one is inside your body poking protons, spinning them round, trying to give them angular momentum. It's stuck there always. This, however, loses angular momentum, which means that the analogy is not perfect. So if I don't do something with it before it runs out, it doesn't work anymore. So last time I'm going to spin it up, and then I'm going to point it against gravity, and you'll all be absolutely amazed when, lo and behold, nothing happens. Hooray! So here is a bike wheel. Angular momentum is aligned with gravity, and everyone is disappointed that they've stayed this late to watch this lecture. However, we can do something else which is useful. We'll spin it up once more. Probably lots more. I find this so much fun. This time, instead of pointing it against gravity, I'm going to have it perpendicular to gravity. And now something interesting does happen. So I'm now not twisting this at all. This is its natural motion. And this motion is called procession. It's a really strange phenomenon that only really happens with things with angular momentum when you are applying what we call a torque. So a torque is just a force, sort of, well, gravity is applying a torque to this. So it's suspended in the middle, and at the end of the wheel, gravity is trying to pull it down. So it's like a twisting force. And as it slows down and loses its angular momentum, it's slowly going to relax back down to its equilibrium position, which was pointing against gravity. Whee! There it goes, almost there. And that's it. Now its energy is lost and it's back to pointing it to its equilibrium position. Now that motion is exactly the same thing as we see in protons. So if you have your protons and they're beautifully aligned with your magnet, as they lose their energy to the system, they keep in their angular momentum, but as they lose their energy to the system and exchange their energy, it relaxes back to equilibrium. So that's what we would normally call T1 in an NMR experiment. Okay, so it's the same thing that we're seeing. Now, the thing which is interesting with this, aside from the fact it loses its angular momentum, and for years I've tried to work out how to get a motor to stick to this so that we could have it with permanent angular momentum, but everything's always too dangerous to keep. We'll try again and we'll spin it up. And I want to show you one more thing with it. So here we have it processing, but I can also now apply another torque to the system and I can make it change direction. So I'm just going to push it round in the circle, and as I do so, it's actually going to tip over. Now I'm not trying to tip it, and in fact, if I try and tip it over, it won't work. It will just fight. I have to push it 90 degrees to the two things that are happening. So angular momentum's this way, gravity is this way. So in order to make it rotate around, I have to push it that way. And this is exactly the same thing as we see in NMR. You have B0 in one direction, and then if you want anything to happen, you have to apply your radio frequency pulse 90 degrees to that, or nothing happens. So if I have an RF coil, let's start this way this time. If I have an RF coil and I apply it at the same angle as my B0 field, nothing will happen. Okay, everything needs to be 90 degrees to each other. There it goes. Okay, so that's the most important thing for us from this. A, this weird motion, which we call precession, and B, that everything needs to be 90 degrees to each other for anything to happen. So our gravity in one direction, our torque in the our angular momentum in the other, and then a torque in the final direction for us to rotate. Same for NMR or MRI. If you've got your B0, your main magnetic field one way, you need your RF 90 degrees to that for anything to occur. Okay. So I will share the screen again. Share. And there we go. Okay, so thinking again then briefly about the physics of this that we've got going on. As I say, our angular momentum is along kind of through the bike wheel. Our torque is applied along the length of that. So depending on where you suspend it will depend on how much torque gravity is applying. And actually that's then the same. So that's our equivalent of our Nmr frequency. Our frequency of precession is driven by how long away from the center of the wheel I was actually going to suspend it. So if I'd suspended it much further away, it would have precessed much more quickly because gravity would have applied a bigger torque. Okay, and that's exactly the same thing as we see in MRI. So the expression for that doesn't really matter. It's a cross product of the torque and, well, it is the torque. So the cross product of gravity and the distance. We see exactly the same thing in NMR, MRI, all things magnetic resonance. So this is Felix Bloch and this is his equation. So the change, in order to change the magnetization direction, so this is a vector, you need to apply some kind of torque, which we're doing here with B0. But any magnetic field to something which has a gyromagnetic ratio like a proton will experience a torque. Okay, we're getting there. So this is a really nice little simulator. You can find it online. It's a Bloch simulator. It's from DRCMR. It's a really nice tool to play with. I've just taken a little video clip of it so you can see what this looks like to our spin system, but it's really good fun. You can play with different field strengths, RF amplitudes, different pulses here along the bottom. I urge you to have a play with it. It's good fun. So we're just going to apply a hard 90-degree pulse, i.e. our spin system is aligned with B0, and then we're going to apply 90 degrees to that, an RF pulse, and our spin system will tip over, hopefully. So here it goes, aligned with B0, tipped over, and then it will precess back again to equilibrium quite quickly because our T1 is relatively short, and it was then ready for its next experiment. Okay, so exactly the same as with the bike wheel. I tipped it over and it relaxed back to its equilibrium position, which is facing down to gravity with a relaxation constant, a bit like T1. Okay, so to do an NMR experiment, this is our favorite sample for learning about MRI, the humble pair. It works really nicely for all sorts of things. You can actually image it really easily because it's very wet, but it's also got an interesting shape that only really matters in one dimension. So when you start to do 2D things, it all kind of makes sense. So to do an NMR experiment, we start off with something, a nuclei with non-zero nuclear spin, so in our case protons, and we put it into a big strong polarizing magnetic field and wait long enough that our spins become polarized. Not very many of them, so we're looking at 0.00001 or 2% at 1.5 Tesla, so it's a tiny quantity. We will then get bulk magnetization, so everything lined up together-ish, which we call M, and that's opposing B0. We then put a radio frequency amplifier into our radio frequency coil, and that's going to make a radio frequency pulse 90 degrees to that. And it's at the moment a nice sinusoidal function, and its frequency is the Nmr frequency for our magnetic field, so we are on resonance. Once that's happened, we turn it off, and then we listen very carefully to what's happening in our system. So we'll have our processional motion. We've got a copper coil around our sample, and as our spins process, they will induce a current or a voltage in our coil, which we then measure, and that's our Nmr signal. Okay, so if you think about our things basically going around in a circle, we are looking at the signal which we're going to get out, and the signal which we get out is a sinusoidal signal. So you can see that on here, the red curve at the top is positive when it's to the right, so facing plus X, and the bottom one is Y, which is positive when it's facing upwards. And as our spins process around in a circle, we'll trace out those curves which we see there. Okay, so our sinusoids make sense because we've got something which is traveling around in a circle. Now, the reason this is important is because everything that we're going to look at from this point forward is some sort of sinusoidal signal. And to start off with, it's sometimes a bit abstract as to why it's a sinusoid, but anything where something is traveling around in a circle is sinusoidal. Okay. So, deep breath, we've finished the bit now, which everyone else has spoken about. So now we're ready to start to go on to the imaging part. So if we just put our pair into our MRI scanner and put it inside, all we've learned about so far is enough to give us this kind of ring down relaxation signal, which you can see here. And the relaxation of that, as we learnt about in the earlier talks, is T2 star. So that's the natural dephasing of the spins relative to each other in the transverse plane. So they've not yet relaxed back to equilibrium, and they may not do so for a couple of seconds yet, but they have lost their phase relationship with each other. What we're going to look at now is how we move on to the next bits, which is to build up an image instead of having this kind of one signal from our whole sample. And that's really the thing which MRI is good for. If all we wanted was to look at the signal that we get from the bulk of our material, we need not go near the MRI at all, because there are better tools for it that cost less money and are easier to use. But if we want to look at what's going on inside and how things vary spatially, then MRI is what we're after. Okay, so a quick history lesson before we get on to how we actually make an image. So on the left-hand side of our picture here, we've got the people who are largely credited but not uniquely responsible for developing what they called at the time nuclear induction. So this is around 1946, and this went on very much to be the start of what we call NMR today. A lot of stuff happened in between this point and what we really call NMR today, but the kind of idea here was very much about identifying chemicals and looking at material properties. We then move into the middle, so 10 years later, and this is Gabiard, and he is almost never credited with anything whatsoever to do with NMR, because he didn't really play an enormous part in it, except for the fact that he was the first person to localize spins in one dimension. And that's a massive achievement and a massive big deal, and he was so enthused with what he'd done, he never did it ever again, got his PhD in it, and then went off to go and build magnetic levitation trains and kind of other exciting things that were nothing to do with NMR whatsoever. But without him, and actually Mansfield and Lauterbur there have said that without his kind of spin localization, neither of them would have done MRI, because it was his thesis that kind of opened up the door to this localization process. Then something interesting happens, which is nothing for ages. And it's not then until the 70s where we actually start to see imaging. And that's when stuff, for this talk at least, starts to get really interesting, and we start to move into what we're going to look at now. I think Gabiard had the right idea, and so we're going to do the same thing, and we're going to start with 1D localization of spins because it's the kind of simplest entry point into imaging. I'm aware that 1D localization of spins is not necessarily enlightening as to what it means, so we're going to have a look now at this. So when I say 1D profile or 1D localization of spins, what I mean is we've taken a system and we're going to look at each of the points along a line to see how much mass there is or how many protons there are or what our signals are. So to demonstrate this, I have again our humble pair. This was meant to be my lunch when I did this video, so I was quite sad not to get to eat it. Here we are, and I'm now going to mark it up into 5mm slices. The idea being I'm going to take profiles of this and I'm going to build up a 1D profile of this pair without any magnetic resonance in sight whatsoever, just by cutting it up into slices and weighing each of the slices. Now, this is not a particularly interesting video to watch this late in the day, so we'll skip forward a little bit. Here are my marks, and we'll cut it up a bit into the individual slices, and each time I cut a slice, we'll weigh it. And each time we weigh it, we'll write down how much the mass was, and that's going to give us a graph, which is our 1D profile. A 1D profile of mass, nothing to do with MR, but a 1D profile of mass. Okay, and this is the thing which is the first experiment we will normally do if we're working towards building a system with imaging. Step number 1, can you do NMR? Yes, excellent. Step number 2, can you get a 1D profile with it? Because we only need to do one more thing than we were already doing to achieve this. So we'll skip through a little bit more. We go into amusing fast motion anyway. Here you can see the pair all sliced up at the top, and we're building up our results. Hopefully none of these are particularly surprising. On the right hand side, where the pair was very thin, we don't have very much mass. Then we build up lots of mass as we come into the kind of big chunky bit of the body, and then all of a sudden it will drop back off of the end. You will see a classic spurious result as the last result, because I couldn't actually manage to cut the last slice into 2, so it weighs twice as much as I thought it might do, but hey, that's science. So if we take this now, we can draw a graph, and this is our graph that we can see here. Now, the reason that I bothered A, to slice this pair up, and B, to show you it, is I want you to see something which again always comes as a surprise when we start doing 1D profiles. What everyone wants to see with a 1D profile is a shape that goes along exactly like a pear, gets wider and then comes back in again, but that's not a 1D profile. A 1D profile is like this. It's like we've weighed each of the slices of the pear, and the more mass there is in that individual slice, the bigger the graph is. So actually, in the kind of meaty bit of the pear, it jumps up twice as quick as you would expect it to, because there's twice the amount of mass if you think about it from the center to the edge, which is what we would normally look for in an image from the top. So a 1D profile is the sum along a dimension rather than what you would see in cross section. Okay, moving on. How do we do it? So this is then the start of actually our imaging. So at the moment, we've got our system and we've just got a big magnet. That means wherever we are in our big magnet, the field is exactly the same, okay? And in our MRI, actually, the magnet is truly exceptional, and pretty much everywhere inside it until you get right to the edges, B0 is genuinely almost the same everywhere, okay? We had it shimmed so that we could do spectroscopy in it, and it really is a lovely, lovely magnet. So we're assuming in the middle is B0, which would give us a processional frequency. Remember how quickly our spins are going around, of gamma B0. To the left is gamma B0, and to the right is gamma B0. So far, everywhere is gamma B0, and all we're going to get is our ring down FID again, our little wiggle, which isn't going to tell us anything about localization. So what we need to do, knowing now that we know that the stronger the field is, the faster our spins will process, is we need to come up with some kind of way to make it so that everywhere in the scanner is not gamma B0. Okay, it doesn't matter at the moment what it is, as long as it's not gamma B0, because if we can work out what it is and where it is, then we can kind of back calculate to get everything else. Now, it turns out that one of the best ways, or the easiest ways to achieve that, is to make it so that in the middle we still have gamma B0. At one end we have gamma B0 plus some more, and at the other end we have gamma B0 minus some more. Okay, so we have this nice linear gradient which varies negative at one end, 0 in the middle, and positive at the other. Now this is one of the key kind of concepts to MRI and making it work successfully. We have in space changed the value of our magnetic field. We've not changed the static magnetic field at all. It's always there, it's always B0. We've just added and taken away from that field to give us a variation in the magnetic field which we're seeing inside. And that's going to give us a difference in how our spins are processing based on where they are in space. So we normally write that as saying that we have all of this is times gamma, B0 plus a gradient. And in our physicsy notation, to say we've got a gradient, we have some kind of coefficient, which is our strength of our gradient, multiplied by our position. So we define the position in the middle to be 0. This is a negative number. So over here, we will have B0 minus a number. And over here, we will have B0 plus a number. Okay. The idea now is that we've managed in space to localize by way of frequency where things are, and I'm sure none of you are impressed by that because we still don't know what we're going to do with it, but trust me, it's what we needed to do. So we now have this system exactly the same as before, our radio frequency amplifiers. This time we've added in this audio frequency amplifier. So this is for our gradients, and our gradients switch much slower than radio frequency, and it's actually what makes MRI make the noise that it makes are the gradients switching on and off to put these different fields in our different dimensions. Again, up here is how we would normally notate it in physics, although to be honest, it doesn't really matter. Just to say, again, to stress the point that B0, our big magnetic field, has not changed and has not gone away. It's just that we've added a little bit to it or taken a little bit away from it, depending on where you are. Okay. To kind of work out what happens next, I want to start off with our simple example, and we're going to take our MRI scanner and we're going to put into our MRI scanner 3 discs which are meant to be infinitesimally thin, so thin that they've got a single proton of water in. Obviously that would give us no signal, so somewhere in between a kind of fat disc and a normal disc will allow us to see better, hear what's going on. So I have my system, and into my system I can place up to 3 discs of water. One of the discs is in the middle, so where I should have B0. One will have B0 plus some gradient when I turn the gradient on, and one will have B0 minus some gradient when I turn them on. To keep things interesting, my discs have different amounts of water in, but we'll come to that in a little while. Okay, so I want now to see what happens when I have my system on and my gradient on and my discs of water inside. And to start off with, we're just going to have our single disc, which is at B0. And lo and behold, this is ignoring relaxation. Lo and behold, we will just have a single frequency of output. And this single frequency of output here is gamma B0. Nothing exciting so far. However, when we put in our second disc, things start to get strange. Here is my second disc, and here I don't see 2 overlapping waves. I see the wave which we had before, which was gamma B0, but I also see it's now got this strange kind of pattern in it. Okay, now this strange pattern we see all of the time in acoustics and physics and music. So anyone that plays the guitar or a stringed instrument might be familiar with what we call a beat frequency. So if you've got 2 things with very similar frequencies near each other, you can hear them interfering with each other. I don't know whether or not you'll be able to hear it over the microphone, but we will see. Let's have a go. So if we pick 2 notes which should be very close to each other, we'll try and bend down. Okay, I don't know if you can quite hear them. They're nearly the same. And now if we make one slightly less the same, okay, you might just hear it wah, 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 over the top. And that is those 2 notes interfering with each other. And that's exactly the same thing as we see here on our signals which we've detected. Now, the reason that I say this is because this is one of the things which I certainly found most baffling when I first started MRI. you have all of these signals, and surely if you just add them up, you should see all of the signals which you had before. But unfortunately, it's not what happens. And when two signals are really close together, they interfere with each other, and this interference is what we see. And this actual envelope of this plot that you can see on here is this beat frequency interference. So unsurprisingly now, hopefully, if we put in our third disk, it's just going to give us more of this weirdness and change our shape entirely again. Now, anyone that's ever seen an image of the kind of signals which actually come out of the MRI, they still don't really look like this. And that's because almost never do we put in 3 infinitesimally thin disks of water, because it's not interesting. We normally have a real sample, and there's this continuous distribution of frequencies all through it. And actually they interfere with each other so much that you just have this kind of bloop, and it drops off and you can't really see anything. Okay? All you get is a bit of the kind of fundamental wiggling which we've got going on there. So we need to do something different now to be able to get from our wiggles that we've got on the left here. So this was our 2 disks. I want to do something to that to get back to 2 lines which represent our 2 disks. Now, we've seen today this used backwards. So to get into our kind of space where we're looking at the spectrum, it's exactly the same as what we're doing here. We've got a signal which is in the time domain on the left here, which is the signal which we've acquired, and we want to take that into the frequency domain so that we can see the peaks which we've got. And we're going to use the same technique, which is a Fourier transform. So this is Fourier, and Fourier came up with the Fourier series and lots of magnificent stuff to do with transforming things from frequency domains into time domains and backwards. But actually, they're almost completely useless to us, and we never really use them. What we actually use was invented or credited to be invented by these 2 chaps, although plenty of people did it in between. And these are Chuki and Cooley, and they actually came up with what we call the fast Fourier transform, which is a useful way of taking some signals. We just do it in MATLAB. You take some signals, you tell it to do a fast Fourier transform, and a spectrum comes out of the other side. And that's thanks to them and several other people, rather than Fourier, although we still call it a Fourier transform. Okay, so let's go back to our signals. We have a single disk, we Fourier transform it. Now we have a single peak. Hooray! This was our old system, so this is 100 megahertz. Now we add in our second disk, we get our strange beat frequency appearing. Now we have 2 peaks, hooray! And this one is 2/3, or maybe it's a half of the height of the first one, because we had half of the amount of water in our disk. Then we add in our third disk, we Fourier transform it. Hooray, we have a 3rd peak. And this one now is 1/3 of the height. So these each have an amplitude based on how many protons there were in the disk. Okay, now this is all well and good. Again, this is not the experiment which we normally do. We normally do things like pairs. So if you put your pair in the MRI, the signal, unsurprisingly, perhaps now looks like this, a kind of disappointing drop off of a wiggle, big right at the beginning and then tailing off very quickly because everything is interfering with everything else. However, if you Fourier transform it, we end up with our 1D profile of a pair. Once again, not like a top-down cross-section of a pair, but basically how many protons there are per slice in our pair. And actually, just for fun, we can stick over the slices that I'd weighed of pair over the top of this, and you can see they kind of line up. It's not the same pair. The first one's completely pretend and made up in MATLAB, and the second one is a real pair, but you kind of see the same shape going on, just to prove that this really does work. And that's exactly what we've done. We have weighed with NMR the number of protons per slice for our profile. Okay, so this is my favorite thing of MRI altogether. We call this process frequency encoding. Now, frequency encoding is basically saying that we have encoded in frequency something. So in our MRI, we have encoded in frequency space how many protons there are in a given slice of pair. But we can do the same thing with sound and basically encode a picture in sound. And instead of having our position in space as our x-axis, this time we're going to have time. So our sound is going to change over time, and it's going to give us pattern in the other dimension based on the frequency of the sounds. So this will be our first kind of 2D image, if you like, but we're cheating and using time as one of our axes. So I'm just going to play one of these for you, and then I'll set up something so we can actually see it. Okay, so hopefully now on your screen, you can see that you've just heard a frequency encoded message. So our x-axis is time as it scrolls past, and our y-axis, the higher the frequency, the higher up it goes. Okay, so we can have a little bit of fun with this. You can see my voice on there now. We can do in real life, and you'll see that the higher the pitch of my whistle, the higher the sound will go on that display. Now, obviously, the problem that we've got in real life is that we can only display one of those at once. And this is a really good fun demo. If you ever get the opportunity to do this with students in a classroom, you can try and get them to write messages by whistling stuff on the board. It's remarkably entertaining. But for our purposes, I just want to show you the kind of displays that we're seeing from the frequency encoded messages which we're making with the MRI. So I've got a couple more because I think it's such good fun. If you listen really carefully, you can hear the high pitch ones and the low pitch ones coming together as it comes around the water molecule. And it's the same thing that we're doing. So if you've got lots of signals at the far right hand side of the scanner, they're going to have a higher frequency than the ones at the left hand side of the scanner, which have a lower frequency, at least on everything we've looked at so far. Okay, we should just do, we'll do two more. I can't help myself, I'm sorry. So that's our pair. And then the final one, which I couldn't get to come out very well, it didn't like the colours of the logo. I'm sorry. Such a quality of frequency encoding there. So you really can encode anything that you like with this. It's actually it's used in a couple of different places. So some people encode stuff in the top, the inaudible part of the frequency range. Aphex Twin have all sorts of profane messages written in the top of their music using this technique, and you can't hear it, but it's there if you play it back through one of these kind of spectral displays. So that's frequency encoding. Exactly the same as we're doing in MRI, it's just we're using time as our second axis. We don't really use time as our second axis very much, however, in MRI. We tend to do something slightly different. So in order to get our second dimension, we do something which we call phase encoding. Sorry, so if you think about what's happening with our spins, and this one is a slightly abstract concept, so I'll go through it a couple of times and hopefully we'll all arrive together at the end. If you think about all of our spins processing around at the same frequency, they will stay in phase with each other. If, however, I make them so that the spins on the right process slightly quicker and the spins on the left process slightly slower, over time they will drift out of phase with each other. At the point at which I stop with my gradient, they will keep their phase relationship and go back to processing at the same frequency. Okay, so we use that to do something called phase encoding, and I've got a little animation which will hopefully show us that now. So on the bottom, we've got our three spins. The top is our field intensity, and at the minute it's the same everywhere along our scanner. In a second, I'm going to stop it before it gets there. In a second, I'm going to apply our gradient. we're going to have a positive gradient on the right-hand side and a negative gradient on the left-hand side. And then we're going to see our spins process quicker on the right and slower on the left. Oh, it started again from the beginning. That's irritating. Okay, so they're all moving together. And then when they get around 3/4 of the way around, we'll pop our gradient on. Okay, here's our gradient. Our right one will process now more quickly and our left one more slowly. And you can see it's racing ahead and getting in front of its friends. The middle one hasn't changed, it's still exactly the same, and the left one is much slower. When we then turn the gradient off, they'll go back to processing at the same frequency as before, but the right-hand one stays as far in front as it was when we finished, and the left one stays as far behind, because they're now moving at the same frequency. The joy of this is that we can reverse this process now by putting the opposite gradient on. So the fast one will go as much slower as it was fast. The middle one still hasn't changed, and the slower one will go quicker to catch up. And then once they're finished, they're all going to process around together at the same frequency and at the same phase. The point of this is kind of key to how we really do MRI spatial encoding. So we have, and you've seen this frequency encoding, and that's really nice, but phase encoding is actually quite a bit more powerful. So if I turn a gradient on, not for long, just for a little bit, and then turn it off again, I will encode in space different phases in all of my spins. And they will keep that, whatever happens, as long as they don't move around. Okay, so if you've got samples that do a lot of diffusion or physically move like a person, things start to get a bit more complicated. But for our pair, for example, I put an encoding gradient on my pair. The pair will then process quickly at one end, slower at the other. When I turn that gradient off, it will keep the phase relationship that it has, and that will be unique in space to the slices that I've got in my pair. Now, the idea with this is that it gives us really good control over the signals which we've got and the signals which we're going to read out based on where they are in space. Okay, we've got a gradient which is linear, it's 0 in the middle, it's big at one end and it's small and negative at the other, or big and negative at the other actually. And so I have a perfect distribution in space of these points, each of which has a slightly different phase. So on here I had 3 and one was ahead and one was behind, but actually all along my sample I'll have exactly that same thing, but each one of my spins will be a little tiny bit further in front of its friends. Now, the idea with this is we can actually build up a 2D image using just phase encoding. Okay, and we have here a thing which people normally call K-space. I'm going to call it frequency space for the minute because it's what we're going to use it as. In that, as you move to the right-hand side of my graph here, it's because I've got higher frequencies represented by bigger gradients. Okay, so as long as the gradient is on, I will be in space, in this frequency space. The stronger the gradient, the further to the right of this graph I will be. However, the thing which is important to realize here is this remains true once I've turned my gradient off. And this is the thing which makes K-space a really useful thing to have. So we have this system here, and you'll see in a moment that the images that come out of it look completely nonsensical, but we've used our Fourier Transform and they turn into our beautiful pictures. But whilst we're collecting stuff, if I want to move to the right-hand side of my graph and collect a picture, I need something which gives me a greater amount of phase change, and that thing is normally a bigger gradient. Okay, so I could move very slowly from left to right of my graph by having a really little gradient on, and over time I'll just increment tiny little bits of phase, or I could shoot from one side to the other by having a really strong gradient that's not on for very long. Okay, so it gives us the ability to move around in this frequency space which we're ultimately going to Fourier transform. Now, there's a really nice tool which I'm going to show you, which you can download for yourselves and have a play with at the link here. It's called K-Space Explorer, and it's a really nice, it's written in Python, it's a really nice tool, and it gives us an opportunity to see what's going on. So on the left, I've got my object that I've placed into the scanner. It's not particularly exciting at the moment. It's a white square on a black background, so this is just a white square. And this software then is going to Fourier transform it and show us what it would look like in K-space, which is what's on the right-hand side. Now, unlike the graph which I just showed you the top right corner of this graph. So the bottom corner of the graph which I showed you, which is basically no phase change, is the very center of K-space, and that's here. To move to the right of this, I need a positive change in phase, i.e. a positive gradient. To move to the left of this, I need a negative gradient, or a loss of phase. When you're thinking about the spins which we saw before, we would have, for the gradient which we'd applied, our spin on the right hand side that had accumulated extra phase, I got in front, would appear on the right hand side of this, and then our one that lagged behind would be on the left. Okay, but we achieved moving around this by applying these gradients. The thing then which is interesting with K-space, I do know a couple of people actually that can tell you what objects are based on looking only at their K-space. I am not one of those people. But if you think about what's happening here, in the middle are signals where we've got things that have experienced no change in phase. That's our kind of big bulk parts of the signal. And what that means is, if we, let's see if I can find the right one here. Come on. Oh, it doesn't want to slide. There it goes. Oh, it's very slow to update, sorry. Come on. And now it's crashed. The things, you can do some fun things with K-space. Hopefully in a minute it will reappear. There we go. And by blocking out different parts of K-space, we can actually filter out our image. So I've blocked out the middle bit here of K-space, and all of a sudden we've lost all of the stuff which is inside my square, and I've just got the outside. And that's because we're doing a Fourier transform, the stuff that's on the edge of K-space corresponds to things which change quite quickly. So this is where you see our change from a dark thing to a light thing very suddenly, which is the edge of our square, appears towards the outside of K-space. If the program will let me swap these over now, and we just look at the inside, i.e. we trim out the edges, here it goes. Over time, the image should get more blurry until you take it too far. It will start to get blurry because we've not got those quick changes. What we have got still is our things which change quite slowly. Now, the reason that I want to show you this is because a big thing that we're going to look at later is actually you don't need to collect all of this information. One of the things which everybody always struggles with K-space is it feels like we've got the same number of pixels in K-space as we've got in our final image, and it should feel like somehow they map 1 to 1. And if you collect this one, you've collected some arbitrary pixel in your image. Is not how it works at all. Every point in your image, if you pick one single pixel, has used every point in K-space to work out what's in that pixel. And that's why we need this fast Fourier transform rather than somehow trying to do it from a Fourier analysis by hand. Every single point makes up every single point in your final picture. Okay, so let's just pick something more exciting, like a pair. So this is the K-space of our pair. This is obviously not what it would look like if we'd scanned a pair, although if we'd taken a cross-section that way, where's my camera? Here. So this would be what we would see for a cross-section like this. You see now we've got these details changing in every direction. So working from the middle of our image outwards, I see quite a few different colors through here, and I get a sudden sharp change at the edge, and a different change in this direction, and a different change in the other direction. So unlike our square, which was just a cross, because we only saw changes this way and this way, we now see this kind of pattern which goes everywhere across the image. And again, if we play with cutting out middle bits and edge bits, if we lose the middle, all we see is these kind of edges, things where our image is changing very quickly. And if we cut out the edge, we will retain our kind of slow changes, what we might think of as our kind of bulk of our color information, perhaps in the pair, but it will start to get blurry and we'll start to lose the edges as we collect just the core of K-space. Okay, the final thing then which I want to show you on here is K-space has this weird property. Some of you may have already spotted it on here, some of you may know about it, which is K-space is pretty much symmetrical. Okay, we've got here an image on the left which is very much not symmetrical in all dimensions, but our K-space area, as I say, we've got things that are changing quickly around the edges and our kind of bulker, bigger color information in the middle, and actually it's completely symmetrical, and sometimes we can use that as a trick. So on here, maybe I don't want to undersample. I want to not take so much information on the edge. Okay, and actually you can still tell that's a pair, but I've now cut off half of the time it takes to do my experiment. And actually I can take off quite a bit more and it will still look like a pair, because we've still got loads of our spatial information encoded within the bits of case space that we've collected. You can also do a different thing, which is to collect half of case space and then mirror it back again. I don't think it will let me do it on the pair. And you can collect half of it. Here we go. And it still really looks like a pair, as long as we collect that very middle point. Okay, and then the most fun thing to do, we've just padded that with zeros. We can choose to not do that and mirror case space about the middle. And actually you build up an image which looks exactly like the pair did before. It's just a bit more noisy. Okay, so we can exploit the fact that it's symmetrical and basically make up the other half of case space based on the information which we already know. There is some magic involved in collecting the important bits of it. And actually there's a whole new branch of MRI opened up in the last 10 years or so of people doing compressed sensing and picking important points within case space that they know will give them the information which they want, but save huge quantities of scan times. Fortunately for the likes of me, who like to program stuff on the scanner and do stuff on the scanner and not do the really hard maths that go with it, they just give you a routine and you stick it on and it works out which points of case space you should collect and it does it. Okay, so we're at that stage very much with compressed sensing, which is really exciting, and it gives us a really quick way to collect images sensibly in whatever directions we want. What we're going to look at now is a quicker way to actually look at the third dimension, and this is one of the things that Mansfield did which got him the Nobel Prize, actually, was this clever way of doing slice selection. So we've seen quite a bit of Fourier transforming, and we know that Fourier transform takes us between a frequency space and a time space. So if we have a cosine or a sine and we put it into our Fourier transform, we just get 1 point, like we saw with our thin disks. If we have a sinc function, which is this strange looking one here, that corresponds to what we call a top hat, so a nice square section. If we have a Gaussian, you get a Gaussian, and this double exponential is a Lorentzian. Okay, but the one which we're really interested in is this second one down, the sinc function to this square box. The reason is, if we were to apply a sinc function in time, in frequency space, we will end up with this square box. And this square box, funnily enough, is a really nice shape to have as your slice. So if we excite our system with a sinc function, we will excite a rectangular section of spins whilst we've got our gradient on. Okay. Now the the figure which we've got here is obviously a person, but it works equally well for a pair. Your top point here is our RF pulse, and it's represented by this square, but it should really be a sinc function. That sinc function has a bandwidth, and by changing the shape of the sinc function and how far out its ripples extend from its edges, we can adjust how wide a selection of frequencies it excites. So by changing the bandwidth of our pulse, we can change how thick a slice we will excite. If we have a very long, very wide pulse, we will excite a very narrow slice, because Fourier transforms make things shrink and expand as you transform them from frequency to space. So a long pulse gives us a narrow bandwidth and vice versa. We can then shift left and right along our gradient by just adding an offset to the center frequency. So we know that in the middle we've got gamma b0, over here we've got gamma b0 plus a bit of gradient times its position. So if we were to set that as the center frequency of our RF pulse, we would move our slice over here to the right and we would be looking at knees instead of abdomen. Similarly, if you were to reduce the frequency, we would move over here towards the head. The other way, obviously, you can do that is by using a less strong gradient. So we're always thinking about the Nmr frequency. So if the gradient is weaker, we will have increased or decreased our Nmr frequency by less, so we won't need to go so far. Okay, and actually that's one of the things that really limits what we can set on the MRI scanner. If you want to have these really to image slices that are really far apart, you need to be able to have a gradient which is either very, very big with big shift in the RF, or the other way round, which is very small and then have a huge change in frequency. And actually it ends up impossible. So on a lot of the clinical scanners like ours, you'll just have a movable bed. So you can image over, we can do slices over 500 millimeters. If we want to go to 600 millimeters, you have to move your thing along, because you can't actually manage to get the bandwidth, frequency shift or gradient which you need to be able to move off of the edge of that. Okay, so we have different ways that we can move through K-space, and we have a different way to pick a slice. So now let's think about how we actually get an image and how we build up K-space. Our order of events is normally that we do slice selection first, i.e. when we apply our 90-degree pulse, our excitation pulse, we're just going to excite a bit of our sample that we care about. I'm going to leave everything else alone. Okay, so if we were sticking with our pair, we might set it so that our slice is here, and we're going to excite the spins in that one plane, and everything else will be unexcited. We can then manipulate everything in the pair, but the only things that aren't pointing along our B0 are these things which we've excited. Okay, and they're the only things that will respond. So we normally start with slice selection, and we do that by applying a gradient and applying our 90-degree pulse or excitation pulse. And then we'll step through X and we'll step through Y using whatever techniques we want, be it phase encoding and frequency encoding. Okay, so we're going to start with the simplest pulse sequence, and it's one which we actually use quite a bit for things that have got really short relaxation times, and it's something called single point imaging. And so this is a representation of our K-space, and in order to collect an image which looks good, I would like to collect each one of these points in K-space. Okay, so I need a way somehow to move around this grid and collect the signals which I need. I always think this looks a bit like Pac-Man. So Pac-Man is now going to come along and eat up each of our points in K-space, and we're going to measure the signals as he goes. So we always start off in the middle, because the middle represents no gradients. So if no gradients are on, all we will collect is the single center point in K-space. However, if we apply a small gradient on X, he'll jump a little bit to the right, and we turn it off and he'll stop moving. And we can make a measurement and then do the same, and he'll walk across one step at a time each time we blip this gradient, and we'll collect one of these points in K-space. We can move the other way, so I've got a negative gradient in Y and he's dropped down a line, and then we can have negative X gradients and he'll munch his way back across, and by doing this eventually we will collect K-space. It is very, 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 very slow, but if you Fourier transform it, you will get back to the image which we should see. The problem with single point imaging is every single one of those points needs an excitation pulse and us to wait for T1 to relax again. And that takes forever. However, it still is very useful, and we will see right towards the end actually that it's amongst our sequences of choice for things with really short T2 relaxations, because your entire sequence is dedicated to collecting a single point. And then you change everything and you do it again and you collect the next point. But you can really focus in on getting the best signal that you can from each of those individual points. So that's single point imaging. Fortunately for us, with people at least, and things like pairs and very wet things and things with very long T2s, we can do much better and we can collect things much more quickly. So this is a book. It's very good if anyone is interested in MRI. The reason I put it on there is because it has 1,040 pages, and this is a book of pulse sequences, and it's like 3 pages per pulse sequence. So that's how many there are. The idea is that for everything we might want to look at, there is a pulse sequence, and people are coming up with new ones all of the time, and some of them are really clever and good fun, but there is a different way to do this for everything. What we're going to look at is the 3 tricks that we can do, and they will make up every single one of those pulse sequences. It's just how you apply them and where you wait and things will change what they're looking at. But actually, there are only really 3 or 4 things that we can do. The thing which is important to realize, and I've briefly mentioned this, but we're looking, when we apply a gradient, we're applying a phase shift to our system, okay? And if we think about the maximum thing that we're shifting, if I put on a really strong gradient for not very long, it will be shifted by exactly the same amount as if I have a very small gradient that's on for a very long time, okay? So it's the area inside our gradient that makes the difference. Short burst, I move very quickly. Slow and low, I move very slowly, but I will get to the same place. Okay, and that's really important for the ways in which we can move around, or as we normally say, traverse K-space in order to collect the points that we're interested in. So here comes Pac-Man again, and we're going to do this time a gradient echo. Now, the idea of a gradient echo is we rely on the fact now that instead of collecting a single point at a time, which takes forever, we're going to try and collect a whole line. So to do that, we're going to move quickly. That's not what I want. Over you go. Go on. There we go. We're going to move very quickly to the left-hand side of our picture. And so we're on the far left of K-space, and we did that with a strong negative X gradient. Once we've done our strong negative X gradient and we found ourselves over here, we can now have a very small gradient, but that's on for a very long time. And hopefully he'll wander over nice and slowly, and each point we collect a little bit of data. This has all come from one excitation pulse. So this now is 11 times quicker than it was when I was collecting just a single point at a time, okay? So I've done 190, I've excited my system, I've moved over to one side, and then as I've moved along, we normally call this a readout gradient. You have a really little gradient on, and we collect the signal as we go, and we'll get an echo, and that echo is the amplitude of each of these points. We can then do as we did before, and we'll have a little blip in Y, and then we'll have our readout gradient again, and he'll munch backwards. And as he does so, we'll collect our signals in K-space again. And one line at a time, we can now read out until we get our whole image again, which we can Fourier transform, and it will give us a square. This, however, is now much, much, much quicker. And actually, in some systems, you might be able to read out 2 or 3 lines at a time before you need to do another 90. The thing that we have to be careful of is all of the time that we're doing this, our system's relaxing, and it's trying to get back to equilibrium with T1, but it's also dephasing with T2. And if we don't do this quick enough, one of those things will happen first and our signals will disappear, and it will make K-space stripy. Stripy K-space in itself isn't actually a problem, and one of the things that you can do is collect every other line of K-space as a way to speed it up, but you reach a point at which it starts to interfere with the image and you get weird artifacts. So what we would normally do is try and work out as much as we can about our system first before we start to do these tricks to collect lots of K-space quickly. Okay, so that was 190, a little tiny gradient to move us, and then a long slow gradient to read out one line at a time or several lines at a time. We can do this then not just with gradients, but we can also do it with echoes. So we called that a gradient echo. This is a spin echo. So just like the spin echoes which we've seen in the previous talks, if you have a spin system and it's relaxed with its FID, you can apply a 180-degree pulse and everything will work backwards. Okay, so the analogy which is often used is this hare and tortoise. They run off on starters' orders, and then at some point the person calls them back again. The rabbit will run back as quickly as it ran away, and the tortoise will come back as slowly as it did, and they will both come back to the line at the same time. Okay, exactly the same as we saw with our refocusing of our gradient, but this time driven by our RF inversion. We some years ago did this with people, which was really good fun, and we had some people on bikes and they ran around on their bikes, and some people walked. And actually, if you count the number of people in the red box as they come backwards and forwards, this does work really well. We also captured an interesting first echo, which is diffusion weighted just like in real life, which I thought was really neat. And then as people get the hang of it, we'll start to build up beautiful spin echoes each time we're refocused. Now, the idea here is we can do exactly what we did with the gradient echoes, but this time with an extra 180-degree pulse. And that's going to give us a completely different way of visualizing our system and a completely different way of collecting our images. And it opens up a whole new area of pulse sequences for us. So actually, almost all pulse sequences are considered to be the gradient echo, because a gradient has said you need to come back now because I want an echo, or because an RF pulse has come back and said I want an echo. So we're going to have a quick look now at our spin echo sequences, because they do something which is slightly different, which is the last bit of the puzzle that we need to do whatever pulse sequence we want. So here comes Pac-Man again. We start in the middle and we're going to jump off to one side with a quick gradient. This time we've jumped over to the right hand side, and you will see why now. So an FID has happened and we've not bothered to collect it because we didn't want it. What we're going to do now is we're going to apply our 180-degree pulse. Now, a 180-degree pulse not only inverts the spin system, but it also inverts k-space. So in addition to making our spins travel backwards, we're also now, after a 180-degree pulse, just going to mysteriously hop over to the left-hand side of k-space. Okay, so any 180-degree pulse will mirror you in k-space. It mirrors about the middle. So if we were up a line, we would now be down a line on the left. If we were up 2 lines on the left, we would be now down 2 lines on the right. Okay, so it just swaps over the middle. And then we can do the same thing again, a little readout gradient, and he will munch his way across and collect some k-space points. We then have a little blip gradient, just like before. We'll go up 1 this time, but now when we apply our 180-degree pulse, he's going to mirror about the middle and he's going to come down to this 1 below the middle, ready to have another gradient, which is going to munch over and collect some more k-space. From that point, we then don't actually need another blip gradient, because you can just hop again over the middle of k-space and he'll come to this next row. And so we have this jump backwards, forwards, collecting 1 line at a time. And actually it saves you a little bit of gradient, and it allows us to have a different kind of control over our collection of k-space. Once again, once you've done that for all of your points, we Fourier transform it and we will still get a square because I've still used the same k-space. But the idea is that we have these ways of speeding up what we're doing. And this was something which, again, actually Mansfield was quite instrumental in doing. And we call this technique echoplanar imaging. So these are the different trajectories which we've used. So this is one where this was our gradient echo one, which we looked at. So you have a little bit of a hop every time, blip, 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 blip. You get to the end of a row, and that will just travel us backwards and forwards. You have another one where you don't actually bother to turn off the readout gradient at all. It's just on all of the time, and you just kind of bounce backwards and forwards in a zigzag. This one is a little bit harder because you don't collect all of the points in Cartesian space. So if you think about my Pac-Man grid, I've got 11 by 11 points and I know where they are. With this top trajectory, I don't actually quite know where my points are in terms of that grid. So I have to give them each individual locations, and I'm a big fan of knowing where things are. So for me, this one is always a bit of a headache, whereas the nice kind of blipped EPI is quite easy to understand. A much quicker way to sample k-space is this spiral EPI, and this one's really neat. It also makes a really exciting sound when you listen to it because the gradients build up bigger and bigger and bigger as they go, and it makes an exciting noise as it spirals out in k-space, which in itself is quite exciting. But we start in the middle as always, and then we have both of our gradients on all of the time, and we have this spiral trajectory. This one takes advantage of the fact that k-space is symmetrical from the middle to pretty much whatever direction you move outwards. So actually, there's not very much information in these corners that we're that worried about. As long as we've got the spokes up and down, we collect lots of information where we really care about it. It's very dense in the middle, and you can move it out and become less dense as you go. It gives you a much quicker collection of k-space, captures all of the bits that we really care about, and does so really, really quickly. So we'll often use this one if we want to collect a whole image from a single excitation pulse. So when we do neuroimaging and you want to look at brain function, this is the sequence of choice, because we might get an entire image. It'll be low quality and pretty low resolution, but we can get images like this in quite a bit under a second, and then it gives you really high resolution in time. So it's a nice technique where you've got things like brains which relax quite slowly. Not so good for chocolate, which relaxes really quickly, because by the time that you're halfway through your spiral, T2 is already 1 and you've got no signal. So they're really good. Pear, very, very good. Chocolate, very, very bad. Okay, so a very quick reminder, hopefully we know lots about relaxation, but the relaxation with T1 is back to equilibrium and is normally for wet things on the order of seconds. T2 is the dephasing in plane, normally on the order of milliseconds or microseconds for solids. And again gives us our first kind of loss of signal. In imaging, we're seeing the difference between relaxation time. So at any time that I do an image, I will see contrast based on the difference between these different levels of relaxation. So if I wait indefinitely and allow my entire system to relax back just enough that I've still got some signal, everything will look very similar, and it will only be weighted by how many protons there are in each thing. So the maximum amplitude that T1 gets back to. If we image quite quickly, then we won't have very much in the way of changes because of T2, but you will have quite a few in the way of changes because of T1. So there's some magic in where we actually collect our image. And what you'll often see in pulse sequences is we'll do what we call preparation. So you'll do a 90, maybe a 180, and wait a bit, and then collect an image as quickly as you can, and that whole image will have a weighting either for T1 or T2 or proton density. Okay, a very quick thing which we do a lot in MRI but not so much in low field stuff is to not use a 90 degree as our excitation pulse. So we have such a beautiful magnet and such beautiful coils, and everything is so beautifully set up, and we have lots of signal because we've got a really strong field, that actually you don't need to do a 90 for a 90. You can tip plenty of your magnetization into the transverse plane by doing 5 degrees or 10 degrees, and actually that's enough to collect some nice signal. Only instead of having to wait 2-3 seconds for it to relax back to equilibrium, now I only have to wait 100 milliseconds, so I can image really, really quickly. SNR suffers, but actually in the grand scheme of things, it's not too bad. Okay, so hopefully you've got a bit of a feel, albeit a very quick one, for how MRI works. I just want to touch now on the reason why MRI is a nuisance. So this is a cantaloupe melon, and this represents about the largest thing that exists on Earth before you start to re-radiate radio stations from your body. If I stuck a melon in the MRI scanner, all is well. If I stick a watermelon in the MRI scanner, I'm going to start to pick up the radio on the MRI scanner. It's not so bad on this one at 63 megahertz. On our old one at 100 megahertz, it perfectly corresponded to our local radio station. And we once tried to decrypt it, but couldn't quite manage it. But we used to get dots on our picture at 100 megahertz from the local radio station if we had a big sample in there, because it just picks up the radio signals in the kind of wateriness of its sample and re-radiates it. So our big scanner and lots of MRIs have to be in a Faraday cage, which you can see here. So it's all copper lined all through the walls, and they pick up the signals and re-radiate them outwards, so we don't pick them up in our sample. In the grand scheme of things, it's not that much of a problem. It gets installed when you have your scanner installed, but there's lots of closing of doors and sitting away from it, and it's sometimes nice to just sit with your benchtop instrument and dip samples in and take them out and be connected with it rather than isolated from it in another room whilst it runs. So that's one of its problems. The second problem is when you want to do these wonderful fast imaging sequences, which I've showed you, and you have samples that are tasty, like this club bar, which I had for my lunch today and tried to image. And if you image it with the fast EPI sequence, you get absolutely nothing. The scanner wouldn't even set itself up. It had to have a bottle of water in next to it so it could set itself up with the water, which I've cropped off. But this is the actual image which I collected of the chocolate bar. However, we have already seen the solution to the problem, which is to use a slightly different sequence. So the first image which it wanted to run out of the box was to collect the entire image from a single excitation, and the relaxation of the chocolate and the shortbread is far too quick and it just sees nothing. You can then override it. So I collected 9 points of k-space for every excitation, and you can start to see that there's something there. It's still kind of noise. And actually, I wouldn't call it a chocolate bar, but there was a thing. If you then drop it down to 2 points in k-space per excitation, you can make out that there's an actual thing there. At this point, we're only twice quicker than we would be if we'd not bothered to use an EPI at all. So kind of wondering why we bothered. And actually, the solution is to use sequences which are meant to be done on things with short relaxations. So this is my flavor of the month on the scanner. Actually, it's a sequence called Twist, and it has a clever they call it random, but it's really not random. It's quite cleverly informed sampling of k-space. It's an early implementation of the compressed sensing, and it picks some clever points of k-space so it can concentrate on the bits that give us nice signals. And actually, if you look at the image, it looks like the one when we put the high pass filter on k-space, and you could see the edges really well, but not so much of the details. That image took 40 seconds to collect. SPI, single point imaging, lots of signal from the chocolate bar, really, really good. This, I'll just flick back. It says club on the top. You can't read it because I had to bite the end off to fit it in the Petri dish to put it in the scanner. But it has some detail on, and you can see that there is some texture to it. So this single point imaging definitely wins. It's quite noisy. It's only one average, but it did take 6 minutes to acquire. So if you have long T2s, it's much better to use the rapid imaging, and it gives you really pretty pictures and you can average them and they look really beautiful. But actually for stuff with short relaxation times, chocolates and those kind of things, you're somewhat limited to pure phase encoding spin echo sequences, which just take a bit longer to run. Okay, so I just wanted to show you our scanner a bit so you can get a feeling for what it's like actually running it. I did this very much in the wrong order when I was preparing, and I should have scanned the pair first. Instead, I cut it up to weigh the slices before I scanned it. So this is the sliced pair now going into the scanner, but you can see it here on its bed, ready to be scanned. It's always important to check on your patient. So this is it on the patient view camera, having been inserted into the bore. And then I'm just going to show you a couple of quick videos so you can see what actually happens. On the MRI scanner, unlike with a benchtop instrument, you know that the sample is in the coil because you've put it into the coil. On the MRI, it could be anywhere in the bore. You just can't see where it is, and the scanner needs to know. So the first scan that we'll always do is called a localizer, and it just gives you a single slice on the system, and it knows where it's got a little laser crosshair, so it knows that it should start in the ISO center, like right in the middle of the bore, and then we have to line up everything else from there. So we're going to start with this from the first point. You can hear the chirping in the background. That's the cold head, so that keeps the liquid helium as a liquid in there and saves us quite a lot in helium replacement costs. We then set up, let's just go back because I was chatting. We're going to line up now 3 different planes onto our pair so that we can have a look and actually see better in 3 dimensions where we're going to scan. And hopefully in a second that will scan. Okay, so it does 3 slices in each plane, so you should hear 9 wheres. Okay, and that's now scanned 3 slices in each of the directions of our pair. Okay, it's a quick gradient echo. It's not a particularly pretty image, but it helps us to set everything else up. Excuse me. Now, what I wanted to do was to then go through and get the same graph as we got before by doing a 1D profile of the pair, which we'll try, and hopefully we'll set up. I think I put the same one in twice. That's very foolish. Nah, there we go. So we've now got our localizer, and we're going to copy over this sequence here, which says it's 64 slices because it's meant for scanning other things. We don't want to do 64 slices. We had 19 before, so we need to set it up and drag it around a bit, and it takes a little while. I hadn't really realized when I was cutting up the pair that I was cutting it up to the pair's axis along the core rather than the axis that I would then use on the MRI. So in a second, we'll have to rotate it round so that it looks sensible. Add 5mm slices, so we'll set that. Some of those parameters will look like parameters that you'd normally set on a low field system or a time domain system. You've got repetition times and echo times and those kind of things on there. But this is the critical part which we would normally do, which is basically to line stuff up. One of the big problems that we have with MRI is this is very much designed to scan a person, and Siemens put a lot of effort into making this scan people really well. It makes it really quite difficult to scan not people, and it fights you at every single step of the journey to desperately try and get you to scan a person, and it wants them to be certain weights and certain sizes and have certain amounts of signal, but we can override lots of those things. So we're just going to make that a sensible time. So that's now 3 minutes. We'll hit apply eventually. Come on, there we go. And now you'll hear it run the scan. We'll pop into the magnet hall so you can actually see what's going on. So this is it setting up. It does some calibration, works out how strong the 90 should be, the 180 should be, does a bit of pretend shimming by working out where the gradient should be strongest and smallest. And after a while, it will finish doing that. Then it will test to make sure that you're not going to give your person too much RF, which makes a ticky noise. It didn't really like the pair. It took it a while to shim. Yeah, Mum. Okay, that's the DICO test, so that makes sure that everything's okay. That then sets up one more spatial calibration for the coils, and then it will run our actual scan. So each one of those is a little segment of K-space that it's collecting for its excitation. And you can hear it thump. So the gradients, whilst they're on, knock against the side and make the noise. And then it will do that until it collects the image. So that's the joy of MRI. So each of the different sequences makes a slightly different noise. After a while, you become accustomed to them. I'd once had one in a hospital and then was really pleased because I'd worked out all of the sequences, but the technician was less pleased. But it is quite exciting. Okay, so we'll have a quick look at some applications now, just to finish off, of different things that you can do with imaging specifically. Now, there's a big overlap between the stuff that people do in time domain and the stuff that people do in imaging. And the key really is imaging is the best thing to do if you want to look at where things are in space, or if you want to do lots of a thing at once. So we've had a couple of projects in the past where we've done recipe development. And it's really good for recipe development because instead of having to put in 1,000 samples one at a time into your time domain instrument, you can put 1,000 samples all in the scanner at once and hit go, and it will just step through them. And there's a load of data and it's painful to analyze, but you only have to do the experiment once and you just collect everything all in one go. So the first one we're going to look at is quite an old paper by Laurie Hall about the kind of general MRI of different chocolates. So this makes for quite a good fun quiz, but I'll let you have a look in the paper if you're interested in what they are. But they basically took a load of chocolate bars and imaged all of the chocolate bars just really to demonstrate that it's possible, and to see a bit about the migration of the different components within. Each one of these scans is a true, normal, proper spin echo image, so relatively slow. It's one slice, and for each of the one slices is 8 minutes, so certainly not an accelerated technique. but you do get really quite nice pictures, and there's some recognizable on there, some less so, and you can see things with nuts in always show up really bright, so we're particularly good at seeing oily things. And if you think about our relaxation curves that we saw, where we've got two really different relaxations, gives you this great contrast. If you've got loads of things that are quite similar, they'll all come out the same color. So obviously our nuts, which are very oily, have got a much longer relaxation time than our chocolate, which is very short and very hard. So you get these really bright nuts and much darker kind of chocolate coating. Similarly for stuff with softer fillings and kind of filled with creams and those kind of things, I'd think 21 is probably a Mars bar at a guess. So you've got kind of soft things inside which have a nice bright signal, and then the darker signal around the edge for the chocolate. So that's nice. They went then on to do a slightly more scientific thing with it, and they looked at the evolution over time of the changes in the T2. So here they're looking at the migration of things from the filling into the chocolate. And this is one of the things which MRI is just great at. So you can watch one sample for a week and see what happens to it. It's not like time domain where you're having to cut bits off of it and pop it into the instrument. You get to keep the same one. So no one ever gets to say, oh, well, maybe it's because you only looked at one sample. You can look at as many as you like, but you get to follow that unique sample all of the way through its journey, which is really cool. So unsurprisingly, they found that things that are filled with soft things, the soft thing gets into the chocolate. So not surprising, but a really nice demonstration of the technique. Another thing which MRI is used quite a bit for is for imaging fruit. So fruit's a really nice thing to image. It's very wet and it looks beautiful. This is quite old now, but it's still my favorite application for MRI. I'm a big fan of process line stuff. So I think MRI has a real great potential for watching things as they're made, as they're processed, and then making decisions. It's hard because you have to be quick, but this was some work by UC Davis some time ago, looking at cuties, which are a type of seedless clementine from the States, which is argument enough to look at this as a technique because that's quite sweet. This is them being sorted, and they come in and they are a seedless clementine. That's not because they're seedless, it's because they've been sorted in the factory so that the only ones that get boxed don't have seeds in. Now, this is normally done with imaging, and they shine a bright light through, and if there's seeds in it, you will see that there's black spots and they'll dump it. And that goes for juicing. Seedless clementines cost a lot of money because they've been sorted. So if there was a way to not dump the ones that actually didn't have seeds in but showed up as a misregistration and got dumped for juicing, then there would be more profit. So they did this with an MRI scanner here, and they would go in one side, be imaged very quickly, almost whilst they're still moving, then be popped out and then go for juice or package, depending on what they were after. On the left is another, this is not from the original work, but it's the same idea. So you can see here an image where it's really optimized to see the seeds, then you can segment them and say, oh yes, that's where the seeds are, and sure enough, that's what they are in real life. This was actually their image from the sorter, and you can see that one's got a seed in, so would need to be dropped. They then did some clever statistical mapping that worked out statistically based on a standard clementine, whether or not it was or wasn't standard, and anything that wasn't per the reference would show up green to red, and anything in those middle segments meant that it had a pip in and should be chucked. They got up to half of the speed that they needed, but they could never quite get over the hill to be up to full capacity. So as far as I'm aware, it didn't get adopted, but a really nice demonstration of the technique. As I say, its real power is in following the same sample as it goes. So this one is for curing meat. It's soaked in a brine solution. The top of the images is more concentrated than the bottom, and you've got T1 on the left and T2 on the right. And as it cures, as the brine is absorbed and the meat shrinks down, then you get this change in T1 and T2, both of which become shorter, which both make sense, as we learned in the last talk. But the thing which is powerful with this is you get to see not only that it is happening, but also where it's happening. And actually some of the things sometimes come as a surprise because we think we know, and it's not actually until you see it happen that you realize that some really amazing things have happened when we would normally have not yet taken a sample, because we have the ability to follow the same one as it goes. So that's quite a nice one. Same idea, this one's freezing. This was trout, I think it's some sort of fish. This is a cross section of the fish which are all stacked together, and they've been frozen for different amounts of time. So D0 is unfrozen and then frozen for 1, 7, 21, 29 and 41 days. And there's some imaging done and then some processing done on the right. And you can see this is actually looking at how the water's diffusing up the fibers, and on the frozen one, all of the fiber bundles are beautifully intact and there's not much free water. From day one of freezing it, the water starts to come out of the cells as they burst in freezing, and you actually start to see this kind of unpleasant mess of nasty fish. So an interesting way there to look at freezing. We did a similar project some years ago on pork pies to look at how they are when they're frozen. So this is a very British beast, very delicious, some pork meat inside, and it should have this nice kind of smooth texture, not mushy, and largely dry. When you freeze them, if they've not got enough salt in, they turn into horrible dry bits of meat and pockets of mushy water, and it's foul. You can tell by eating them, we all got absolutely sick of eating horrible pork pies, and actually MRI can show you straight away whether or not it's going to be disgusting. Delicious on the left, absolutely gross on the right, and it's just a really nice way to see without having to eat stuff. So MRI is the saviour of the taste panel who have to eat horrible things, and again, we could get in our current system, we could get 30 of these in one go and actually image them all at once to look at different recipes as they were developed. We took it a step further and looked at how the jelly, so they have like a gelatine jelly inside, which is meant to preserve the meat. If the jelly is too thin, i.e. not viscous enough, it seeps into the pastry and makes the pastry soggy. So we did a thing where we looked at viscosity of jelly versus how far into the pastry it had penetrated, and you can see on there the bright bit is where the jelly's got into the pastry and the dark bit is what the pastry should look like. There's a nice linear relationship which taught absolutely nobody anything about how to make pork pies, but it's a nice demonstration of how MRI is useful for these sorts of things. This one is a really nice example of why MRI is not always the best technique. So this is brining of feta, and this is a cube of feta in like an upside down brining cup, basically, and watching how the brine goes into and cures the feta. And actually, with the exception of this image, all of the others are pretty much homogeneous and could have easily been done on a time domain instrument just with a core of feta. So it's nice, it makes a pretty picture and they're really nice results, but actually sometimes MRI is not the best technique. We did one which we presented at MR Food when it was last on, where we looked at cooking bagels in the scanner. So we actually cooked them in the scanner, which was really good fun. We had a boiling bath of sodium hydroxide in there. We had one boiling with vinegar and one with water. And we saw some really interesting things which we still don't really understand, to do with how the so when you put a bagel into it should be cooked in an alkali solution like sodium hydroxide, and as you put it into the water, it first off puffs up and then it will kind of set its crust and then you bake it after. The sodium hydroxide puffs up really, really fast and then collapses on itself and shrinks down into this horrible, disastrous, dense nastiness. The vinegar actually gave us a really nice increase and kind of puff up, which you didn't see with the water. And we think it's because we had too concentrated a solution of sodium hydroxide, but there's some interesting stuff that can be done looking at Maillard reactions on it, which is very much not our area. This is the bit we're good at, and we rely on everyone else to help us understand what's happened. We did a similar experiment with kefir. So this is like a fermented milk beverage, kefir grains, and we looked at different sizes, same mass of kefir, but different size of grain. And I think, unsurprisingly, if you have lots of small grains, you have a really big surface area and the reactions driven on the surface, so it happens much more quickly, and it causes flocculation, so we get a drop in T2 and T1, and that gives us a brighter signal. So the sum of the signal intensity from start to finish goes up, and then we have this kind of weird rate limiting thing on our biggest grains, which we still don't really understand, but again, a nice MRI thing with food. Okay, so to wrap up, a quick summary of the things that MRI is good for. Hopefully you've seen what it does and how it works, and got a bit of a feel for the sorts of things it can do. I think it is the best thing to do if you want to see where things are in your sample. Has this thing moved into this thing? Is this thing where I left it when I put it in? And you can follow the same thing for that whole process, which is nice. It's also really good if you want to do a big panel of things. So we love an experiment where we change two variables and we lay them all out on the scanner, and one thing changes one way and one thing changes the other, and you get a map. Is really nice, and it's all on one image, which makes it really easy to see what's going on and to analyze, and it really accelerates that process. All the better if they've got favorable properties for MRI and they run quickly. The other thing that it's really good for is making a pretty picture, and it sounds very patronizing, but a lot of the time, if you have a pretty picture of something, people are much quicker to believe what you're saying and understand what you're saying than they are when you show them a relaxation graph, or this is T1 and T2, and sometimes having a nice picture of it really helps sell it, and MRI is fantastic at that. Okay, that's me. Thank you very much for your attention, and I'll take any questions anyone has.